Welcome and thank you for downloading the SteerDuff podcast.
Okay, last time I was here I talked with you about lift and drag and thrust and weight. I don't know whether there are some questions about that lecture. Tomorrow you will have some studio classroom event, and then you will have some exercises also about these items. So you will have a look into some formula and so on. I don't have I don't know whether you also have questions about the stability issue. Professor Hoekstra taught you last time, but I advise you to ask him, because he's an expert on stability issues. It was his topic during his graduation, so he knows much more about it and much more fluent than I do. So I will ask you to ask him. Okay, if there are no other questions, then I will continue and tell today something about structures and structural concepts. I hope this is working. Yeah. First of all, if you look into the book of Anderson, there's not much about it. I think even they skipped it from this textbook. There was a chapter about materials and structures, but it was very, well, not of high quality, I think. But nowadays they even skipped it, so, well. Last year I also made a special handout for it, and I will put it also on Blackboard, so you can see it. And that's about structures and materials. So next time I will tell more about, when I come here, that's not next lecture, but second lecture from now. Then I will tell more about materials. Now I will focus much more on structures. You already see here some pictures of structures. Why structures? Well, last time we said, when we were talking about the total weight of an aircraft, that you have three components. First of all, the payload, the weight of the fuel, and also the aircraft empty weight. And a significant portion in that is the structure. The wing, the horizontal, and so on. You may ask yourself, what is a structure? How do we describe that? And how does it perform? Well, you will see that when talking about structures, we also talk about beams and beam-like elements. I will explain that and also talk a little bit about loads. Loads acting on aircraft structures and how to handle them. What is a structure? Is there someone who can give me a first shot? If you would like to express multiple components put together. So at least it's consisting of multiple components and it is put together, some kind of joining or something like that. Yeah? Self-supporting body of 3 dimensions, self-supporting of any kind. Yeah? Anything about functions? What is the function of a structure? Carrying loads of by the components, yeah. More? Okay, I heard at least some elements which you will see also back in the next slides. Actually, the first thing I would like to show is a structure is something like a skeleton. I put a nice horse in here, and you can also see here the X-ray picture of the same horse, of course in different posture, but nevertheless. And you can see the horse has a skeleton which is, well, first of all carrying indeed the loads. All the actions the horse is doing are carried by the bones. You see there are also multiple elements in there. It's not just one bone, but multiple. huge diversity in elements, small ones and big ones. It's not just a heap of bones, but they are nicely ordered, also connected, and so on. And, well, it's not visible from here, but I can assure you, also different materials are used. Yeah. So these are some features, some characteristics of a skeleton. And these are also items you will see in a structure. Structure of a car, structure of an aircraft, structure of a train, and so on. So many elements, several functions, coherence, joints, different materials. Okay, here you see, for instance, a structure of a car, simple car. This is, I think, almost 100% made of steel, but nowadays you see more and more different materials coming in. So some parts are made of steel, some parts are made of aluminum, some are even composite. This is a structure of a satellite. This is just the skeleton, to say so, of the satellite, made of a tubular portion, built of sandwich panels in many cases. Who has been already in the vliegtuighal? Most of you? Vliegtuighal. Okay. If you look, for instance, in the vliegtuighal, there is a very tall, it was very impressive, I think. There's a very tall, product, a black product made of carbon sandwiches, and that's actually a satellite. The structure of a satellite. If you look into it, you see a cylinder, which is more or less the backbone of it. And then you have also a square tube, which is made of sandwich panels. And it's about, well, maybe 10 meters tall even. It's that tall, it can just stand in that hole because of the crane. That's a similar thing as you can see here, but then much bigger. That's the skeleton, the payload, the instruments are built in there. Okay, functions of a structure. What are functions of a structure? We have seen already and mentioned already carrying the loads. What more?
Maybe dividing the load so that not all weight is supported by one point but across several points.
Yeah, distribution of load, so you have load path in the structure. Yeah. Keeping things together. Yeah. Strength, strong, should be strong, should be stiff. Protection, yeah. Well, again, a few of these items are also on the list here. First of all, loads. Structure is mainly designed, in particular in aircraft and spacecraft, to carry loads. We have seen one of the previous lectures that we do have a weight. And in many cases, most of the weight is concentrated in the fuselage, about 60–70%. Particularly if you also have the engines close to the fuselage, then most of the weight is concentrated in this area. On the other hand, the force that has to make equilibrium with the weight is our lift. And the lift is performed by the wing. And you can see there is an off distance between the lift and the weight. Of course, the resultant forces are in the same place, but to carry the lift from here to there, we need a structure. The structure has to carry the load from A to B. And that should be strong enough, it should be stiff enough, and so on. Protection. What you see here, for instance, is a, I think it is an EasyJet Boeing 737, which flew through a hailstorm. And hailstones in the order of magnitude of golf balls hit this aircraft, and you can see you have quite some damage. If you view this incident on the internet, you also see the leading edges of that aircraft, and those are made of metal, so there are a lot of dents in there. Yeah, so that's even some of the windows have been cracked, not broken but cracked. Protection. Yeah, just think again about the horse. A few slides before, we have a skull, and the skull of our head is protecting our brains. Protection. And finally, also, you need to have a framework to attach all kinds of systems and other items to it. This is a fuselage without any systems. Let's say the skeleton, let's say the structure. And this is when all the systems are built in. So that means the overhead lockers, the window panes, all the seats, all the air conditioning systems. The whole bunch is in there, and it is attached and screwed and wired to the skeleton. Yeah? So 3 main functions. Okay, then I'll go back to a little bit to some historic pictures to see also a little bit development. Realize, and I did not tell you so far, but there's also a big influence between the structure and the material. You will see later on. If you design, if you create a structure, you can already see in many cases what kind of material is used. Yeah? If I think about a Greek temple, what kind of material is used? Marble, stone, limestone, these kind of things. If you envisage that picture, such a temple, if I say you make that from steel, you're out of your mind. Yeah? Eiffel Tower, for instance, that's made of steel. You can already see the connection between the use of material used, and also the shape. It's only one, sir? Okay. Okay, so you will see that also here again. That sometimes you have materials like steel tubes, and then you think about truss structures. We will see them in the next slides. Well, these are the old days. We have a lot of cables, a lot of wooden lath. These are these flimsy elements made of wood, fabrics, linen, for instance, to cover up wings and fuselages. Later, more trusses, spars ribs, load-carrying wooden rings. So far, and then I will later return to the other ones. This is a familiar picture. We have seen that before. That's the Wright Flyer. Well, here you see all these wires, these flimsy wooden ribs, you may call it, and also the fabric which is covering the whole system. This is typical from the early days, a structure from the early days. And the strength and the stiffness of that structure is a combination of all these flimsy, fragile elements together with all these wires which are needed to get it rigid and sturdy enough. In the early days, we often saw a lot of biplane aircraft. And these biplanes are there because if you have 2 wings, you can connect them more or less, and that already gives some stiffness and some strength. Does someone know the difference between stiffness and strength? Can someone tell me that? Yeah, more or less, yeah. So the strength is the maximum load, is related to the maximum load a specific structure or material can take. And the stiffness is how far it deforms during a certain load. If I have a very little deformation with a particular load, then I can tell, okay, this is a very stiff, a very rigid material. If I have a very large deformation, with the same load, then the material is flexible, it's very unstiff. Yeah? That's the difference between strength and stiffness. Once I had to make, that's maybe just a story to tell a little bit. I had to make a chair made of laminated materials, laminated steel or aluminum plates, I think it was, for a furniture company. The company was making all kind of furniture for hotels and conference centers and so on. So they were looking for a new chair, and they came to us, to our laboratory, and said, well, you have a new material of laminated materials. We would like to have a chair made from that. Well, we said, well, it's strong material, but it's not stiff. So you have to do a lot of in the stiffness, in the shape, in order to get sufficient stiffness. Well, no problem. We have a designer, and he will do it. And, well, there was something from a professor from Nijmegen, and he had a very nice design, looking very good indeed. But we said in the first place, well, it's not stiff enough. A lot of stories about it. Make a prototype. So we said, well, we will make a prototype, but realize it's not stiff enough. No problem at all. And in the end, we made the chair. And one of the directors of the company was, I think, a big guy, I think 120, 130 kilos. So he came into the room. Is that the chair? Yeah, that's the chair. So he, without any further comment, he just plunged into the chair. Well, we were talking, how is that surviving? It cracked a little bit, it made some noise, but it survived. The only thing it was, he was moving around and getting more or less seasick on that chair. So that's the difference between stiffness. It was strong enough, but it was too flexible. Well, as I said, we promised him that beforehand, but okay, in the end it turned out indeed that we were right. But it was a very nice example. I threw this chair away later, and that's a little bit pity because I could use them in classes like this. Okay, biplanes to support the wings. They can support each other in order to get sufficient strength as well as sufficient stiffness. So you have these advantages. Also the maneuverability of these planes is usually better. Sometimes you see them nowadays with these air races. What's Red Bull? Yes, that's you see them also. These biplanes, because they are very agile and very maneuverable. On the other hand, the effectiveness of having two wings is not as doubling the wing area. You only have a very limited increase in lift there. Later we went to monoplanes, because then we got stronger materials and better concepts in building wings. And you see here a number of wings, a lower wing, a wing at the center section, and a higher wing, and even a wing which is, well, more or less floating over the fuselage, a so-called parasol situation. Again, you see here a wing of the old days, completely made of wood. You have some wooden tube inside and some ribs mounting on top of it. What kind of loads can such a tube take? Think about bending or torsion or tension or compression. Can I put a tension load to it? Compression? Bending? Torsion? So such a tube, such a box is actually quite sufficient for a lot of loads. Later on, when we are a number of slides further, you will see that most of the wing structures have in the center some kind of wing box, some closed area where we also put in the fuel. But that's not only to put in the fuel, it's also for taking up a lot of loads. Okay, you see here this a wing spar, wing box, mini wing box, and some ribs. In the 20s, the 30s, you have this aircraft. Fokker was in those periods, late 20s, very famous. Was actually one of the leading aircraft manufacturers in those days, and this aircraft was very famous. Until there was a crash in 1931, and a very popular sports team also was died in that crash, and there was a lot of questions in the United States. At the same time, you already saw the first metal aircraft emerging, and that means Fokker went out, at least in America. Well, here you see some pictures of his production site in these days. You see, this is, for instance, a big wing, fully made more or less of wood, triplex wood. And in those days, it was not too difficult to get all these workers, because the only thing you need was carpenters. You can make it of wood. The shift to metals was much more problematic, because a lot of people, there were not many people working with thin metal sheets. So they have to train and to educate a new generation of workers. This is the fuselage of the same Fokker 7 aircraft, and you see it is a fully truss structure. Truss means made of metal tubes, welded together. The skin, which is wrapped around it, the linen, did not have any load-carrying capacity. It was just there for keeping the atmosphere out as much as possible, just for a little bit comfort. Testing in those days, also very nice pictures about that. Here you see, for instance, a beam which is tested. What kind of test is this? Well, the stiffness, or maybe the strength. You are going to test its full strength. And then you can tell whether such a beam is strong or stiff enough. You see, it's a very, very simple, simplistic in these first days. Same kind of testing, in this case, testing a truss structure of the fuselage. Put some weight here, put some men here, and if it passes the test, it is certified. Well, nowadays we do it completely different, with much more paperwork, much more instruments, much more, and also takes much more time as well. This, for instance, the wing, composite wing of a Bombardier C series, or Bombardier, composite wing. You see here some hydraulic jacks, and these are attached to this wing and then moving around for a couple of months in many cases. Everything is recorded, both what kind of movements, also the local stresses, the local forces are measured, and so on and so on. So these are huge programs, very costly programs, and in the end, if everything went successful, then you can certify your aircraft. But that's completely different as what you have seen on the previous slides. Okay, so far something about old days. Now I will zoom in a little bit in the structure itself. And what we have said before is that when we talk about the structure, it is actually consisting of multiple elements, multiple components. And if you look very carefully, you will see that most of these items, most of these components, after the break I will bring some, most of these items are derivatives of a beam. A simple I-beam, as you can see here, a top flange, a lower flange, and a web plate in between, a simple I-beam. Most of the elements we use still today are related derivatives to such a beam. So therefore I would like to zoom in into that beam, and first starting with some truss structures. And I'm building it up to a beam as you see here, and so on. Okay. First, as I said, we were flying around with truss structures. For aerodynamic reasons, they were closed with fabrics, but nevertheless, the trusses were the load-carrying sections. And if we look at the basic element, the basic cell of such a truss, actually it consists of 4 elements. Well, here it is attached to the floor, but you can also say there is a 4th element to it. If these are true hinges, just a little force pushing it aside will rotate this shape, and from a square you get some kind of shifted shape, as you can see here. In order to prevent this, what we can do, one way is to remove these hinges, so prevent rotating. We can do it, for instance, by welding these bars, these beams. If you then apply a force, you see still some distortion. Of course, these square angles, the 90-degree angles, remain more or less 90 degrees, but now you get some flexing in your structural elements. So a more elegant way to do it is to put an additional element in there, another beam, another bar, as you can see here. And this is sufficient. Now we do have a static determined structure. Well, if you look at truss structures, they are built from elements like these. Yeah? Building up, this is a starting element, and building up you can continue and make your truss structures. You've also seen on these old slides that we often use a lot of wires. Yeah? Piano wires, for instance. So you could ask, can we also use piano wires? Well, as you can see here, if this is my structure, and here my piano wire, that's okay as long as the load only comes from the left side. Yeah, then the wire is as sufficient as a beam, as a bar. If we reverse the load, if we go the other way around, then of course it does not work anymore. So, your solution is creating a cross. So this is what you see in the early aircraft sometimes. You saw on one of the previous slides, the one which were testing that fuselage of a small aircraft, the man standing on one side and the weight on the other side. That was a typical truss structure using these wires. Later on, when you have the slides, you can look onto it. Okay, so that's 2 solutions. You can use cables, or you can use bars, you can use rods, and so on. So these are equivalent. Both are sufficient. What happens if we are not using one element, but if we use 2 elements? 2 bars. Is there a disadvantage? Is there an advantage? What's the disadvantage first? Disadvantage.
Maybe the space inside the box cannot be used because of the
Yeah, maybe they are conflicting with each other. That's one. Less flexible. Whoa. They have more weight. Yeah, seems to. They are all depending on one component. If one component fails, the whole system fails. That's questionable. More material, more weight, more material waste. Yeah? Some buckling is possible. Yeah. Well, actually, you have two problems with that. First of all, indeed, the weight. You should say the weight here is too much. Because you add a extra bar which is not useful. It's not adding something. And the second one is to get these two bars in the structure. One is okay, that's very easy, because then you have enough flexibility to put that bar in. But if you have to put in the other one, you need also a high accuracy, because otherwise it does not fit properly. So you make it yourself rather difficult to do so. What's the advantage of this one? Very strong. Better stability. Yeah. So each other. Redundancy. Yeah, coming close. What happens if one of these elements fails? Let's say I cut this one. It's still standing, huh? What happens if I cut this one? It still stands. What if all other ones are intact, but I cut one of these diagonal bars? Still stands. So this is what we call fail-safe. Well, I will try to explain that in the next slide. So it is more difficult to assemble. It's more difficult to calculate. Is it heavier? Well, first instance you would say yes. It has some reserve, and that's my advantage. It is a fail-safe structure. Now I will try to explain two concepts what you see in structures, save life and fail-safe. If I have to design a structure for, let's say, 20 years, what you used to do in a safe life arena, you say, okay, if all these elements should work for 20 years, then I have to make them strong enough that I'm sure that during that lifetime they won't fail. That means I have to make them thick enough, sturdy enough, strong enough, and so on. That means maybe I have to make them a little bit thicker than I want to. If I go to the other concept, that's fail-safe, that I have some redundant system. Yeah. If one of these elements fails, still my whole system is performing correctly. No problem at all. The only thing is, as soon as one of these elements fails, I have to notice that. So when I frequently inspect, I can discover one of these elements if it has failed, and I can replace it with a new one. So usually fail-safe comes with some inspection intervals. But if I do it like that, then these individual elements can be lighter than in this case. My safety factors here are higher than in this case. So although I do have one element more in this case, the system as a whole can be lighter. Yeah? Well, this is what we often do now today. Fail-safe. So that means that when you have an aircraft and you operate an aircraft, you have to maintain it. You have to inspect it frequently. So if you go to KLM, they have a big hall where they do all the inspections. You have 4 types of inspections: the A, the B, the C, and the D check. And the A check is usually done on the platform when the passengers are moving in and moving out. The B check is maybe one night at the facility. A C check is maybe a couple of days at the facility. And a D check, or the heavy maintenance, is a couple of weeks at the facility. And then the whole aircraft is stripped, inspected from all sides, refurbished again, and can fly around for another 3 to 5 years without such a main check. So, Most of the structure nowadays are designed with this concept in mind. There are a few items, like undercarriage for instance, that's still designed in a safe life philosophy. You cannot make that redundant. You only have one nose wheel for instance. You are not going to do it twice. Yeah, so there you have differences in design. Okay, going back to our truss elements. We have seen if we have an element like this with a diagonal bar, this is capable of taking up all the loads. These are bars. What we also can do is replace this bar with a metal sheet or a sheet which is taking up all the loads. And that's possible. So as soon as you have bars and you connected a sheet in between, you have also the same rigidity and strength as in this case. In that case, you have here a sheet which is taking up tensile and compressive stresses. In this case, if we have applying a load in that direction, the material wants to deform like this, wants to become longer in this direction, so I have a tensile force in this direction. In this direction, it tends to become shorter. So I will have some compressive forces. So if I have this load, sometimes you see these type of wrinkles appearing. That means elongation in this direction, contraction in that direction. Later on I will show you a nice picture of that. Okay, so far something about one cell. We can extend that. This is a beam with 4 cells. And actually what we do is to synchronize 4 of these cells and we have a truss structure of 4 cells. If I apply a load here, the load has to be taken up by the structure and transferred to these points, to these points on the left side. So the load has to travel from right to left. What you see here is that we do it in this case with some wires. You also can do it of course with these bars. There are bars in here at the top and the lower side and also here in between. And what's striking is that the bar at the top side is increasing in cross section from right to left, both sides. You may ask, why is that? Just looking for someone else? Yeah. The moment becomes larger when you go from right to left. So if the wall was placed here, I only have a very small, tiny bending moment in my beam, with a compression at this side and a tension, or compression at this side and tension at that side. Now I do have a very long, very large bending moment because it's the force times the length of this arm, and it has to be supported, it has to be transferred to the wall via these horizontal lines. Okay, the vertical rods and the wires do not increase in size. Why not?
Is there no horizontal forces applied?
No horizontal forces?
There are, but they don't change in magnitude as in that case.
Oh, sorry. No horizontal forces. We have only one vertical force. How is that transferred from right to left? By the upper beam, or the upper elements, or by the diagonal elements, or by the vertical elements? Yeah.
Whereas in the other way, they should be able to handle that.
Yeah, but what elements are transferring this force to the reaction forces here? The wires? Yeah? So this force is transferred to this wall via these vertical elements and the wires. And what is the size of that reaction force at the left side? Is it larger than my applied force? Smaller? It's the same size. It's the opposite direction, but it's the same size. Yeah? I hope it is on the next slide. No, maybe not. Well, here you have actually more or less the same system, but now you use diagonal bars, and here it is split in forces and bending moments. So if this is my beam, this is my object, what I'm looking for, there's one external force, and that's here, that's this force. What I need now is reaction forces on this end that results in the fact that my beam is maintaining its position. As soon as there's no force and no moment equilibrium, the beam will move, or rotate, or move. Yeah? So first, if I look at equilibrium in vertical direction, I do have a force here, so I need a counteracting force somewhere also in vertical direction. And here it is. This force plus that force means that the whole product cannot move in this direction. Yeah? Enter up with a beam. I started with this beam with a top flange, a lower flange, and a web plate in between. Well, that's what you see here. Top flange or girder, a web plate, and a lower flange or lower girder. So here you see my simplified beam. And what you will see after the break, that a lot of structural elements have a beam-like shape. First, have a break. Okay? Yep. Okay. This was the last slide before the break, so we can continue from here. What we have seen before the break is how to descend from a truss structure to a beam. I have a few slides and I will then show some examples. Again, if you have a cell with a plate in it, you will have some waviness, you will have some buckling. As long as this buckling is elastic, reversible, it's not a problem. Most materials do have some elastic bending, elastic properties. So that means that if you see these buckles, it does not directly mention that everything is failed. Only when it becomes plastic, permanently deformed, then you have a problem. Then your structure is failing. This is what I have seen also a couple of years ago when I flew in an old Dakota aircraft, DC-3. When he made a turn, I saw also this is not, by the way, my picture, but I've seen similar buckles in the wing as in this picture. This is typical what you see sometimes when the plate, in this case the skin, is subjected to what we call shear. The web plate is subjected to shear, has to transfer the vertical force in the beam, and here it has to transfer horizontal forces. And if it has to do, sometimes you see these kind of patterns. I beg your pardon? No, this is made of sheets. So no more wires, no more rods, bars, and so on. Yeah? It's fully made of sheets. Is that what you mean? Yeah. Well, here you see another example, and in this case it has failed. In this case the whole beam has failed, and the buckling you see right now here in these windows is done by plastic deformation of the metal. So if you take it out, you still see the waviness. It's just as if you mend metal sheets in a workshop. Any idea why, for instance, you also have some waviness in the upper girder? Why is that? Gravity? Ooh, not the gravity. Looking for other. The vertical beams? No. Pulling? No. What was the loads if you have a beam? You have one side you have tension, the other side you have compression. And this is the compression side. Yeah. So that's why this top flange, upper girder, we sometimes call it, is subjected to compression. So if it is thin enough, it also may buckle. And that's what you are seeing in this picture. Okay, so far something about the truss structure and the derived beam. Few words about stiffened shells, pressure cabin, and so on. Shell structures arrived when we talked about metal aircraft. DC-2, DC-3 were the first metal aircraft flying around. 1930, in that period, 1940. We also have in the vliegtuighal, there's also a small piece of a DC-3. I think this is one of the wing sections there. If you look at this one, you see now a lot of protruded head rivets. In Dutch, bolkopnagels. No countersunk rivets, but protruded head rivets. That was in the early ages, the early stages, because they were not able at that stage to make them countersunk. Shortly after, 10 years later, they had also countersunk rivets. So you have a flush outer surface. But that in our piece we have in our collection, there's also a part which has these protruded head rivets. And that's very nice because it is one of the first pieces made. Another way of building aircraft from metal is what Professor Jonkers did with these famous aircraft used in the 30s and later also in the war. Corrugated sheet here, as you can see, also providing in itself already some stiffness. If you have that waviness in your sheet, you can also use it to your advantage. Well, this is typical of what you see nowadays in shell structures. You have a skin, which is very flexible, and you have a backup structure made of frames, stringers, and so on, which provides the stiffness. These flexible edges are very easy and very comfortable if you have to assemble it, if you have to make a big structure of it. Because these are flexible, you can adjust them very easily, locally. That's becoming, by the way, more and more a problem if you are working with composites. Composites are much less flexible in these kind of things than the metals. That's also why, for instance, the 787 had quite some problems during the assembly. As soon as you have a mismatch in dimensions of a few millimeters, it is much easier for a metal to accommodate that, to counter that, than for composites. Okay, a structure is made of many components, structural elements as we call them. We have primary structures. If then one component fails, then you could have serious problems, could be catastrophic. Secondary structures like fairings, in many cases, if there is some damage, okay, you have to repair it, of course, but it's not catastrophic. These are also in many cases load carrying, and these are usually just protection or some fairings for good airflow and so on. Most structural elements are, as we say, beam-like elements. Again, this is a typical schematic picture of a beam. Two girders for taking up the bending moment and a web plate for taking up the vertical force. I hope everyone can see it also in the back. This is some kind of floor beam, yeah? As used nowadays in metal aircraft. Many cases you see some holes punch in it just to reduce the weight, but nevertheless this is more or less the shape of it. You have two flanges, as you can see, and a web plate. Actually it is something like a simple beam. Yeah? Another element, if you look into the study collection we have, you see a lot of these stringers. This is what we call a Z-stringer. I just turn it around a little bit so all the others can also view it a little. Actually it is a shape like this, a lower flange, a vertical flange, and then a curl, Z-shape stringer. Again, you have upper flange, lower flange, and a web plate in between. Also a beam-like element. Wing rib. Yeah? You can see here, web plate, upper flange, lower flange, and it's again some kind of beam-like element. In this case you see a lot of colored holes. Those are for reducing the weight, and also a number of these stiffening elements. You can see them even better on this side. And both the color here, the edge here, as well as these ones are for increasing the stiffness of this flat surface. But the basic concept, the basic principle, again, is a beam. I have more beams. The frame of an aircraft. Yeah? Here you have the slots for the stringers to run along with the frame. But again, two flanges, upper and lower, and a web plate in between. Yeah? And even a structure like this, I hope that's a little bit visible also for the people in the backside. This is a sandwich structure, as we call it, made of composites. You have an upper facing and a lower facing, and a core material in between. In this case it is an aluminum honeycomb, and actually the aluminum honeycomb acts as a web plate, has the same function as a web plate. The facings take up the normal forces, the in-plane forces, the bending moments, and the honeycomb, which is in between, takes up the vertical forces. Yeah? So all these elements, and most of these elements you can find them a lot in aircraft, are actually beams, beam-like elements. Okay. Well, just a few pictures to show. Here you see, for instance, a wing box. This rear spar has a girder here and a girder here, and this is its web plate. You also have a front spar. At the same time you see all these stringers, as I told you, these are also kind of beams. Upper flange here, and these are so-called head stringers, so they have two lower flanges, and these vertical areas are two web plates. This is a wing, fuselage structure. Again, you see here the frame I showed you. You see some stringers I showed you, and here you see also a fuselage structure. And again, you see a lot of these frames and stiffeners running in this direction. Floor beams. And all these elements are more or less alike each other. A wing box, again, and all these elements, well, if you look at it later when you are at home, you will see most of these elements can be derived or related to our beams we have discussed so far. Last question, last comment I would like to make here is a load path. How to get a force from this end, the red one, to make equilibrium to that one. You need to have a load path. This is a vertical force, so I need to establish a path, a path from here to there to make that equilibrium. Since it is, in this case, a vertical force, I have to think about it that I need to have elements with web plates from here to there. The first part of the track of the path is provided by a stringer. The stringer has a web plate. The second part of the track is provided by a rib. A wing rib has also a web plate. And the last part is by this spar, which also has a web plate. So then my load path is there. So I can transport, more or less, this vertical force to the roots of the wing to make equilibrium with the one who's coming from the side, for instance. Yeah? Same you have to do if you have a bending moment. Same you have to do if you have a compression. Same you have to do if you have a tension, and so on. All these loads need to have, you have to think about in load path. Okay. Questions so far? Okay, then I will talk a little bit more about loads, and I will try to do it a little bit quickly. This is what we call a so-called speed load diagram. This is a frame, a window. An aircraft has to be staying within it. Yeah, if you design an aircraft, you also design a window like this. In here you see a lot of loads, and the load, as you can see here, is defined, the load factor N is defined as the lift over the weight. As soon as I'm flying around with a high load factor, let's say 2, I have a lift which is twice as high as my weight. That means I'm taken up. As soon as I have a lower value than 1, then of course I will go down, or gradually, or if I'm in a dive, very significantly. Well, that's the load window you have to stay on. Any idea what the load factor in cruise is? Just 1. So somewhere here on this line. Another thing I have to mention about loads is that you have, in many cases, a so-called limit load defined and an ultimate load. And the difference is a so-called safety factor. Limit load is actually the maximum load which occurs once in a lifetime, and at that occasion your aircraft may not be damaged anyhow. So no permanent deformation, no failure, and so on. Ultimate load should not happen at all, but starting with a limit load, we apply a safety factor, let's say 1.5 or 2. That means the load twice as large as my limit load, an aircraft has to sustain for at least 3 seconds, and after that it may fail. Those are 2 design things we work with when we design and build structures. Sometimes this one is decisive, and sometimes the other one is decisive. Depends a little bit on what kind of material you are using. Here you see, for instance, behavior of materials. In one of the next lectures I will explain it in much more detail. But this is typical force displacement curve for a metal. You have some elastic behavior up to the yield stress. And as long as I stay within that yield stress limits, the material can be used many times. Yeah? It always reverses to its original position. As soon as I surpass that, I come into the plastic zone, plastic area. We don't want to fly in that area, because then you have permanent deformation of, for instance, your wings. Well, that's not recommendable. But this is, by the way, if you would like to make products, like the ones you see here on the table, if I would like to press form a wing rib, then this is the domain I have to work in. So for operation, for using, for flying around, this is my domain. And for manufacturing, that's my domain. Yeah? Composites is completely different. Composites doesn't have any significant plastic deformation. So you have elastic deformation more or less until failure. And that can be rather tricky. So you have, in many cases, for composites, higher safety values than for metals, because it's more uncertain what you're doing there. Well, sometimes, I don't know whether you have seen this picture before. This is, if it is working, yeah. I hope the noise is not too... This is an aircraft flying around and shears off, breaks off its wings. What I said previously about the box, the window, yeah, there are much more. There are much more. There are much more. What I said a few minutes before, every aircraft has this window, a flying window, to stay within that. In that particular aircraft, we don't know why, but somewhere went out this window, and then you can see what happens. We have to design and create aircraft with a certain limits. We cannot make everything possible. So there are always some limits. Otherwise you have to make it too heavy. Well, this is a Fokker 27, an old aircraft from the 50s. One of the things you saw in that aircraft was rather revolutionary in that time. For instance, bonded structures, extensive use of adhesive bonding, also some introduction of some fiber composites, and also the introduction of a pressure cabin. Well, that was not completely new for this aircraft, but it was one of the first aircraft who did it. Just to think about the pressure cabin, and then we are talking about loads. This is a significant load for an aircraft, in particular the fuselage. Every time an aircraft is going to fly on altitude, let's say 10, 11 kilometers, it has a significant pressure difference inside-outside. So the pressure difference between inside and outside, this one, can be up to half bar, 0.5 bar. And that means significant stresses in your skins of the aircraft. You can calculate that with formulas like this one. In the hoop direction or circumferential direction, in this direction, it's the pressure difference times the radius of the fuselage times the thickness of the skin. Yeah, actually you have to know this. Yeah. But not tomorrow, but next week there will be some exercises about it, so you can learn and work a little bit with it. But it's not too complicated to. And otherwise, if you have more sophisticated formulas, we will provide you with it. But these two formulas, the hoop stress and the longitudinal stress, are very simple, and you can memorize them. In longitudinal direction, also it's very simple. You have at the end of the cylinder, you have a pressure bulkhead taking up the loads, which have to be transferred by the skin. And here you have the area of the skin, circumference times the thickness, and a stress, and that should be equal to the pressure working on this surface, as you can see here. And when you calculate, it's rather easy and straightforward. It's not too difficult. It looks difficult, but it's not that difficult. Well, that's pressurization. Here you see a typical example. Flying around with an aircraft with a diameter of 2 meters, range of 2 meters, diameter of 4. Flying at 11 kilometers, you have this pressure. If you would like to maintain the pressure at an altitude of 70% of sea level, then you have this pressure. Pressure difference, and you can calculate some stresses. If the skin of this aircraft is only 1 millimeter thick, the circumferential is almost 100 MPa, and that's a lot, really a lot. This is much more common, about 50, 60. But then you see you already have a thickness of 2 millimeters. If I have a bigger aircraft, larger radius, then of course also my stress, if I would like to have the same stress, also my thickness will increase. So a jumbo jet has usually thicknesses of 3-4 millimeters. Yeah? Okay, but you will work with it later on. Different types of pressure bulkheads, a membrane type, balloon type, a bulb type, and a really stiffened one. This one is stiffened with all kinds of elements in order to prevent deflection in this direction. There's a huge pressure force working on it, 0.5 kilo per square centimeter, so that's huge. And I need to stiffen it up with all kinds of elements in order to get it to remain it flat. Pressure cabin is also a pain in the neck for a lot of other items. There are a lot of holes in it. People want to look outside the windows. You have also cutouts for doors and here for the wind. Sometimes also undercarriages and so on. So that's, you have actually a pressurized cylinder and you are going to make holes in it. Well, that is asking for a lot of problems. And that's also the case of the failure of this aircraft, the Comet, in the early 50s. And then we learned actually from a new type of loading, and that was fatigue. Yeah. Before that, we never calculated, we never recognized fatigue until this aircraft. Again, there is a lot of videos to be watched at YouTube. This aircraft was one of the first jet aircraft. Just after the Second World War it was designed, and in that time the British industry was ahead of the Americans. They were much faster in developing these jet engines than the Americans. Unfortunately, they had the problem of fatigue. So a lot of these metal skins were rather thin. They were riveted with self-riveting rivets. So they were pushed in there, and if you have a hole and you push a pin in there, sometimes it cracks at the edge. Well, these tiny cracks, they never thought about it. So during pressurization of your fuselage, again and again and again, these cracks started to grow. And that's actually what happened. So fatigue was then an item. The aircraft were grounded for 2 or 3 years, and in that time the British took over the lead with their 707 and the DC-8, and then they took the lead in the market. And the British never recovered from that setback, actually. Always remains a smaller partner. Few things about fatigue. It is a dynamic loading. It's a alternating loading. Think about the paperclip. You can not break it by your hands, but as soon as you do this multiple times, ultimately it fails. That's also some kind of fatigue. Yeah? Well, here you see, for instance, what kind of loading you can have. Think about the fuselage again. You pump it up every flight, and if an aircraft is flying 50,000 flights or 90,000 flights, you have 90,000 cycles, and those are severe cycles. Also a wing, when it is flying, you have a lot of movement in the wing. These are all kind of fluctuating loads. May introduce fatigue. This is what we call a so-called SN curve, stress cycle curve. Here you see the number of cycles on the log scale, and here you see the maximum stress you can apply to the material. If you only have one cycle, that means we just pull it apart in a testing machine. Then the material can have about 320 megapascal. A megapascal is a stress, is a force divided by area. Yeah? If you go, for instance, to 1,000 cycles, you see the stress has already reduced to 200. If I go to 100,000, then we are at about 120. And if it is 10 million, we are about 80. So that means the more cycles you pull a material, the less force it can take because of fatigue. Fatigue usually does not come in constant rhythm. Usually you have all kind of spectra, as we call it. Well, later on in the studies you will learn more about this, that you have a variable fatigue, you have spectra. Some of these cycles you can ignore, and some of them are maybe small but very important. And how to learn and how to notice these will be told later. If we have fatigue, we know now there is fatigue, we have to inspect. And inspection is also something we have seen before. That was when we talked about the fail-safe concept. You have redundant materials, and if one fails, you have to detect that, to notice that, and replace it. Well, that's also the case here. So fatigue is also a system which is related to fail-safe. If the number of cycles starts, if you have a new aircraft, of course you may hope there is no much damage in there. So we assume in many cases there's no damage. Just after the time, it takes some time before damage, cracks initiate. This is this period. But as soon as it is initiated, we don't see it. We do not see it detected during our inspections. Only when it becomes visible, after this period, we are able to detect these cracks, detect these damages. And we have to detect them before the damage becomes critical. Every crack, every damage has a critical size. And as soon as you reach that, you get a rest failure. The material just fails. The product just fails. So we have to detect it somewhere in this period. So if we know, for instance, for a particular product, typical material, structural elements, this curve, we can say this is our inspection period. Here we can detect damages. Usually we divide such a period up in 3 or 4 periods, and every period we do an inspection. So what I told about the heavy maintenance, the D-checks, that every 3 to 5 years an aircraft is taking apart more or less and inspected thoroughly, is based on schemes like this. Yeah, so that 3 years or 5 years is somewhere related to that period. Has to do with damage development. Okay, fatigue locations, the wings and the fuselage. Well, I already told you, pressurization, and in the wings, all kind of maneuvers, remove, and so on. Okay, summarizing. This afternoon we have talked to each other about structure. Structure is one of the best things I can think of is usually a skeleton. A skeleton of an animal, a skeleton of a human being. That resembles a lot of features which also a structure has. Functions, also talked about from truss to beams and what kind of beam-like elements you do have. And also talk a little bit about some loads. Not all the loads, some loads. Last question. Do you have any questions? Then I wish you a good evening.
Please visit our OpenCourseware website for more information. See you at our next